Our next talk is a joint one with the probability and statistics session. The speaker is Massimiliano Gubinelli from the University of Bonn, and the title is A Panorama of Singular Stochastic PDE.
Yeah, so I would like to thank the Gustavo Pons for introducing me and the organizing committee for giving me the opportunity to speak today to you. And what I prepared is introduction to this field called singular SPDEs. And there will be no technical details, maybe something at the end if time permits. And I will try mostly to motivate, okay, to give you motivation, and especially because these are strange equations, or equations which are not well posed, where every time you try to write them down, there should be some infinite quantity somewhere. And I wanted to demystify these infinite quantities and just show to you where they come from, okay, that they have to be there because these equations are a description of some very specific behavior, which are fluctuation, non-Gaussian fluctuation of random fields, and this infinity actually it's just the remnants from another scale of the problem, which at the scale we are looking at, it's infinite. Okay, so it just happens that it has to be there for some reason. And this is quite recent field of mathematics, which essentially blossomed after Martin Heyer won the Fields Medal and found this very beautiful theory of regularity structures. I will not have time to describe even regularity structure in my proceedings. Essentially, the proceedings is completely orthogonal to the presentation, so you get 2 for the price of 1. And in the proceeding, I'm more detailed about the technical details. Here, I will spend a lot of time talking about motivations. And yeah, technical detail, I will introduce them in this setting of paracontrol calculus, which could be interesting to the PDE community because somehow it's a way to handle this kind of problem where it does not work all the time, but when it works, looks very similar to and uses standard tool of PDE theory. Okay, so that could be selling point for paraproducts and paracontrol calculus, which is introduced in this paper to PDE community. And let me say just that both theories, so regularity structure and paracontrol calculus, they really have initial impetus and motivation from Lyon's theory or rough path theory, which is an analytic way to do stochastic calculus, okay, to solve stochastic differential equations. Yeah, and I tried to put as much reference as I could, but without being boring, okay? So I had to leave away just pedantic list of all the references and try to cut out a nice path in the recent result. Okay, essentially all the results are after 2013, maybe, something like this. So let me start with, so I will give you a certain number of examples, which are microscopic model for which we want to describe the large-scale fluctuations. Okay, and the first kind of models are one-dimensional interface which grow. Here you see some example. This is like some Tetris game which is played by a very inexperienced player like me. And this is some sheet of paper which has been burned and the level of the burning recorded, and you see that there is an interface growing. You can assimilate it to a graph of a function in one dimension. And you see some characteristic, for example, fluctuation increases as time passes, okay? And if you think about, like in Figalli talk about the interface between ice and water, you can single out 3 different regimes depending on the temperature. When temperature is quite high, then there is a real difference between the So ice is not stable at all at that temperature, so you have a very fast growth of the interface between ice and water, so water gets most of the space. And you expect, so in this regime, fluctuation grows like 1 power 1/3 of time. And you expect that this rescale to something which is called Kpz fixed point, which I will not touch about, but just to mention it, and to make the different regimes. So at 0 degrees, so both ice and water have the same energy, so there is no preference at all in the thermodynamics, and you get only fluctuation out of the process. And this is reversible, okay? You have the same chance to become water as to become ice from water. And this is a regime which is well understood in simplified model, goes back to the end 80s, beginning of 90s, and fluctuation go like 4th power, and there is scale to a Gaussian limit, okay? So in models of this phenomenon, you really can prove that the large-scale fluctuations are Gaussian and they have this behavior. And then you can put somehow in between the two, okay, this is too difficult, this is well understood, so you can try, okay, let us be just near reversible, but slightly in a regime where one of the two phases is not favored. And in this case, you expect, what you expect and what you can prove in some model, I will show you, is that fluctuations scale like in the Gaussian regime, but the fluctuations are non-Gaussian. And actually, they are described by what is called the Kpz equation. Okay, Kpz stands for Kerdar-Parisi-Zhang. Here, I just want to make the difference that there are various objects, and you should not confound them. So there is the Kpz equation, and there is Kpz fixed point. So Kpz equation will describe interfaces precisely in this regime, and somehow, if you look at it in certain scaling, also converge to the Kpz fixed point, okay? But there are two different objects. Okay, so let's see, be more precise mathematically. Let's try to write down a simple model. So this has to be understood as a microscopic model, okay? So I will put a small parameter epsilon, so everything is parameterized by it. So you will have noise in this model, which is smooth, nice, with order 1 correlations, okay? And then you put diffusion, so noise, so you see you have your interface, noise model, some growth phenomenon, and you have diffusion, and you have somehow preferential, you have some drift in the sense that if the interface is tilted, you expect to grow it faster. So you have differential drift, which depends on the tilting of the interface. The function f is not very important in what I'm saying. You can think it's just an arbitrary polynomial, and then things are set up so that the equation is well posed. Okay, this is not even an SPDE, it's a PDE with a random source term, because the source term is nice, okay? So you can sample it, it's a nice function, and then you can solve it via PDE method. There is no probability involved, okay? But it's a random field because you have a random input, and I will neglect the initial condition. And you see, here you take small drift, okay? This corresponds to the fact that your temperature in the previous slide was nearly 0, okay? If here, so I'm going forward, if here you take epsilon 0, you have a Gaussian field, okay? So this is introduced small non-Gaussianity, and you would like to look at this model on large scale. And then what is suggested from the question is that you do a transformation where parameters are put in such a way that you keep balance between time derivative, diffusion, and noise, so that you have a diffusion with noise in the limit. And when you do so, there is only one way essentially to do this. You get this behavior for the nonlinear term, okay? The nonlinear term was small in the microscopic scale, but you accelerate time, so this has time to develop and looks quite large in the macroscopic scale, okay? And what happens to the noise term? The noise term, we choose this scaling, so you see you you somehow minimize the interface. The interface is growing quite fast, so you multiply with the factor going to 0. And the noise term is converging to space-time white noise. Okay, this is quite easy to, because you are scaling space and time, and you're taking this this factor, okay, which is coming from the time derivative, essentially. So you see, space-time white noise in this equation is appearing for natural reason. Okay, you are not postulating it. You are just saying in the microscopic model correlation at small scale, when I zoom up, I have to see space-time white noise. And space-time white noise is not so nice because it's very regular. It's not a function. It's a distribution from the point of view of analysis. And this is the first kind of result which I would like to present. Has been proven by Ira and Quastel in 2015, sorry. And looks like following. Okay, there is some, you cook up some constant from the function f and from C0. C0 essentially it's some quantity, some real number which is related to the correlation scale of the noise. Okay, so you look at your noise, you look at your function, you cook up these two numbers, lambda and nu, and nu essentially is some average speed on the interface. So you take your original interface, you remove this speed, you see it's something going to infinity on this scale, and then you center again with some constant to get something normalized in the proper way. And then the result that they were able to prove using the full machinery, okay, this looks innocent, but essentially this has to use the full machinery we discovered only after 2014. Before was not possible to prove this kind of results. The statement does not depend on the machinery, but the proof depends heavily on that. So the random field you obtain converge in law on continuous function to this random field, which is constructed in this way. This is called the off-called solution to the Kardar-Parisi-Zhang equation. What you have to do is to solve the heat equation with multiplicative space-time white noise, and then take the logarithm. You prove that it's positive, you can take the logarithm, so you construct a new random field, and this random field is exactly the limit of the previous one. So in this equation, this is a classical stochastic partial differential equation. Its solution was known since the 80s, essentially. And it's possible to solve it provided you interpret the product as an Ito product. And this theorem justifies somehow this equation. Okay, the equation is the limit of a model which is quite natural, okay, from the microscopic point of view. Okay, you just cook up the simplest model which has all the phenomena you want to look at, and you end up with a random field which has to be solved this. Now, this is a very implicit description because you have to solve an equation and take a transformation. There are other models which converge to the same equation. Okay, the interest of this equation is that it's the limit of many models, and they are completely unrelated. Okay, I gave you two other examples. So this is the first example which was shown to converge to the Kpz equation, which was done by Bertini and Giacomini in '97. This is a weakly asymmetric simple exclusion. You look at particle moving on Z, and you allow only one particle per site, and then particle jumps left and right with probability P and Q, and you take P and Q. So if you take P equal to Q, this is somehow a symmetric model. If you take P slightly bigger than Q, this epsilon play exactly the same role of epsilon in the other model. In this case, in this model, so you have particle, okay? But from particle, you can cook up interface by saying my interface, the increment interface in an interval is just the number of particles in that interval. So essentially, you go up, you construct an interface by going up if you see a particle or going down if you don't see a particle. And then you take the scaling limit of this interface, provided some centering is done, and you converge to the same equation. This was the content of their paper. Another kind of model you can cook up is really different. Now here on every site you have a real random variable which solve a diffusion equation which depends on the nearby random variable. Okay, R are the difference between nearby values, and you depend on the left-hand side and on the right-hand side according to some potentials. And again, here you have P and 1 minus P, and you can produce either a reversible dynamics or a slightly irreversible one. And in the slightly irreversible one has been proven recently to converge to the Kpz equation again. So formally, you can try to guess what is this equation. Okay, I gave you the equation for z, and then told you that h is logarithm of z, and then you start to compute, maybe using Ito rule, and you discover that the equation has a weird-looking form. Okay, looks like Hamilton-Jacobi-Bellman equation with a source term which is space-time white noise, but okay, if you do computation formally and you are not a probabilist, you miss the infinity. If you are a probabilist and you know Ito rule, you say, there is an Ito correction, let me try to compute it, and the Ito correction turned out to be infinity, okay? So that's the problem with singular SPDEs. So the natural equation you would like to write for H does not make sense. So you cannot even start talking about existence of solution because you don't have an equation for start. And it's clear that it's not dual-posed because we have a candidate for the solution. You can study regularity of that candidate and you discover that it's a continuous function of time, but regularity in space variable is just 1/2 order minus something, okay? So there is no chance to give a meaning to this derivative squared. And the additional signal is that there is an infinity there. Okay? And this problem, I mean, this equation was discovered by Kardar-Parisi-Zhang in the '84, but it has remained a very long problem until Martin Heyer gave a solution theory. First, he gave a solution theory based on rough path theory. And then there are other solution theories based on other approach found by Goncalves and Jara even before, but they didn't have uniqueness. Uniqueness was proven only recently. And this is more probabilistic, it's based on martingale problem. Okay, a higher approach, it's really PD approach. You find a Banach space of function where you can give a meaning to this equation and solve it via fixed point method. And then regularity structure somehow systematized the approach that Ira found in this very particular case. And essentially we solved also this equation using paracontrol calculus in a later paper. Let me give you another example, okay? Just want to go on giving few examples of different equations. In this case, sorry, should I miss a slide? Oops. There is a slide missing. Now I'm in big trouble. Yeah, okay, sorry. I mean, there is a slide missing. I don't know why. So let me skip this part maybe, because I will not be able to. Okay, let me try to explain. There is a slide missing explaining the problem. Okay, here the problem is having a Ising model. So you have spin on a lattice, and you make them interact. Usually in the Ising model, you have two choices. You make spin interact with local interaction, so every spin interacts with the neighbors, or everybody interacts with every other, so you have either mean field or local interaction. But you can have a choice in between the two, that is, you choose that every spin in a neighborhood of size gamma, they interact with each other, and you are living in a lattice of size n, and essentially you construct a Gibbs measure and you construct a reversible dynamics according to this Gibbs measure. Okay, the missing slide was the description of this dynamics. And And then you construct a mean field, that is, this is an average of all the spins around a given point. You rescale it, and essentially you choose the inverse temperature near a very specific value. And Murray and Weber proved that in this case, provided this constant is chosen in such a way. So you see this is in between mean field and local, okay? You're choosing every particle interact in average with every other particle in a radius of size epsilon 1/2. And essentially, the lattice spacing is of size epsilon. Okay, so particles interact with a large amount of other particles. In this case, you can prove that the field converges in law to some random field. And you can guess the equation based on the dynamics. So this was a computation which allowed to guess the equation. You have to write the generator for the dynamics, and essentially a computation gives you some expansion like this. It's not very important, okay? Just give you some expansion like this for the rescaled field, the one which has a limiting behavior. And you see the limit, you can guess from here the limiting equation, okay? The field satisfies the fusion equation with a linear term and a cubic term. All the other terms are going to 0, and then there is a martingale term which will converge to space-time white noise. And now, the only other thing I want to show you is that the assumption you're making is that beta minus, you see there is this epsilon minus 1 here, and the assumption on beta is that it's going to 0 fast enough so that this quantity is bounded, but not quite, because this constant is diverging like logarithm of epsilon, okay? So overall, this quantity is slightly diverging, okay? And this is sigma, another sigma that you have to deal with some kind of, so the limiting equation looks like this if you write it formally, okay? It's a reaction diffusion equation with additive source term, which is given by space-time white noise, and with an infinite constant here. Again, this equation, you think 10 minutes, and then you realize that this equation is not well posed, because even for the linear equation, if you forget the nonlinear terms, solutions are distribution, okay? So there is no way in classical functional spaces that you could start even an iteration procedure, because you cannot give a meaning to the cubic term, okay? The solution of this equation at the end of the day will be functions which are continuous in time, but which takes value in spaces of distribution. So let me spend a minute to introduce this, because I will need it later. I use this symbol to indicate base of older spaces, which are spaces of distribution for which every time you take a band-limited decomposition using Liouville parallel function, you get bounded functions, okay, with a prescribed decay of the L-infinity norm if alpha is positive, or if alpha is negative, they are distribution for which you have a control of the pieces, and essentially you can analyze the function as a sum of all these pieces. Every piece is just band-limited analysis of the function around frequency 2 to the I. Okay, so this means that essentially you have to understand these functions are, so kappa is any number bigger than 0. You cannot take 0, but anything it's okay, anything bigger it's okay. So these are almost functions. They are like derivative of functions which are almost Lipschitz. You can understand negative spaces in such a way. Okay, so again, this we find, and in a very you take a very natural model, you take a limit, and you find again an equation, at least formally, which is not well defined. In this case, this is a simple example, because actually in the strongest form it was understood by D'Aprato and de Bush how to solve this equation and how to give a meaning. Similar analysis holds in, similar things can be done in for dispersive equations, okay, and was discovered somehow independently. But for this equation was a contribution of De Prato and de Bush. And their idea was to decompose the equation in two parts, the solution of the linear part plus a perturbation, and to write an equation for the perturbation. Now, the idea, so here I write infinity, and I work at infinity as it was a number. You could imagine that you regularize the equation and you want to take the limit. So think about this is a quantity which is finite and want to go to infinity. But the idea is the following, that is, the solution of the linear equation is a Gaussian random field. And when you expand the cubic polynomial, essentially combinatorics, so this is, at this level, it's a miracle, okay? Combinatoric is such that the infinite quantity distributes in this way, and that you can give a meaning to these polynomials of a Gaussian, okay? These are called weak polynomials. They can be defined via limiting procedure. And at this level, it's really a miracle that things work out algebraically, okay? If the coefficient here was not 3, would not work, okay? And when you single out these random quantities, and then you write the equation for the remainder psi, you actually are relieved, because in this equation there is no infinity anymore, and actually makes sense analytically, because you check the regularity. Essentially, regularity of psi is 2 to the minus 2 minus k, and each of these distributions can be shown via probabilistic argument to belong to space of distribution of regularity minus kappa. And then there is a rule, essentially, in all the Bezout spaces that you can multiply things as long as the sum of the regularity is bigger than 0, strictly bigger than 0. Okay, so every term now on the right-hand side makes sense, and this is a well-posed PDE. Okay, so this is somehow the simplest singular SPDE, which can be solved. It has been solved in 2003 without any sophisticated tools, okay? Because this very simple linear change of variable make the game. I mean, the price to pay, you have to realize that there is a price to pay, okay? The price to pay is that what you believe was the noise term in the original equation is not what is actually the noise term, okay? It's not psi, which is driving the equation. You had to insert some probabilistic knowledge before starting the analysis. And the probabilistic knowledge is that actually the driving terms, you see, in this new equation, the driving terms are 2. These two terms cannot be related in a functional analytic way, one to the other, okay? From the point of view of functional analysis, they have to be considered new source terms which are independent, okay? There is no way to recover this term from that one, okay? Probabilistically, they are generated from the same noise, but if you only look in analytically, there is no way to go from one to the other, okay? They are coming from probability. So the idea of rough path theory, the idea of regularity structure, and the idea of any theory handling this kind of equation is that there is a probabilistic step where you construct like polynomials of the noise term, and then the solution will behave well only as a function of these polynomials, but these polynomials are not good functions of the original source term. And as soon as you cannot single out this term, you cannot solve the equation. Okay, so the first step will usually it's manipulating the equation to get this term out, and then usually you have a well-posed equation. Okay, so let me go on. And now I would like to shift subject because I want to give another example of application where singular stochastic PDE appears. So we saw one-dimensional interface, we saw fluctuation in Ising model with mean field interaction. And the third example will be Euclidean quantum field theories. So in Euclidean quantum field theories, and I would spend one slide to explain what are Euclidean quantum field theories, because I think this subject is quite fascinating. So the goal is to construct quantum field theory, and then in the 80s, essentially mathematical physicists understood that there is a recipe which you can follow to construct a quantum field theory which lives in relativistic space-time. And the recipe is as follows. You start from Euclidean space, that's why it's called Euclidean, and you allow yourself to use the full Euclidean group of RD together with the reflection along the last direction. And so Fg denotes the action of G on the function f. And then you assume that you are given a measure on distributions over Rd such that its Laplace transform satisfies three properties. Okay, first property is that the Laplace transform has to be invariant under Euclidean group. So this is the law of the random field has to be invariant. And then some technical conditions, which are some bounds for this Laplace transform. But the tricky one is this one. This was the new ingredient, which was discovered by Osterwalder and Schrader. That is, you require also that every time you look at this kind of matrices for any given set of functions, so once you take the complex conjugate of the test function, the other time you take the reflection of the function. This function is supported only in positive value of the last variable. Then this has to be positive definite. Okay, this is key ingredient. And then whenever you have all these ingredients together, there is a recipe to construct out of this measure an Hilbert space with an action of the Poincaré group, which is unitary, and also a vacuum vector which is invariant under this action, under the Hamiltonian. And Hamiltonian is positive, okay? So this is a very tight relation between probability theory and quantum field theory, relativistic quantum field theory, okay? You see the trick here is that here you look Euclidean space, and here you get Poincaré space objects, okay? So this is related to the fact that you are using this rotation in a very non-trivial way, okay? This reflection positivity gives you an Hermitian scalar product at the level of the Hilbert space, okay? This is the tool to construct the Hilbert space. It's really reflection positivity, okay? This gives you a scalar product, essentially. And then you say, I understood this, so let's look at measures. Every time I get a measure satisfying this, I get a new theory, new quantum theory, essentially. And then you are very much deceived because it's not very easy to get 1 and 2 together. Okay, every time you get 1, you don't get 2. Every time you have 2, okay, maybe 1 is not so okay. Okay, so this is really non-trivial, and essentially, I took the non-trivial case. So in 4 dimensions, we don't know anything. 2 dimensions is more easy, so I'm taking 3 dimensions. So these are the Euclidean dimensions, okay? It means that this will give you a quantum theory in 2 + 1 dimension, okay? So still not realistic theory. But essentially, the only measures you know which satisfy this criterion are either the Gaussian measures, which have this covariance, so the Gaussian free field in 3 dimensions, or things which are constructed according to Gibbsian recipe. Okay, does not seem so, I'm going back one slide, that does not seem so innocent, but I mean, taking together these two things is quite difficult, and essentially we have only 2 kinds of answers. So either Gaussian, which is not very it's interesting, but it means that the quantum theory you will reconstruct from that, it's free. So will not describe interacting particles. So if you want to have interacting particle, you have to have a non-Gaussian measure. And the only non-Gaussian measure which satisfies reflection positivity can be built in only in this way. But that's tricky, okay? And there are a lot of people contributed to this program. It can be done, but it's tricky because the support of the measure mu is not on functions, okay? So this quartic polynomial, you cannot give a meaning, and then there are other problems, okay? So even you say, okay, let's start discussing a bounded domain because the integral over all space surely does not make sense. And then let's regularize the field by convolution. Then I can make sense of this quantity. This is a measure, but you need to take the limit epsilon going to 0, otherwise you will not satisfy the axioms. Okay, that's the problem with Euclidean quantum field theories. Just you need to satisfy these two axioms, and it's quite difficult. And so let's go to PDE. So where PDE enters into this picture. So this goes back to an idea of Parisian Wu in 81. Which saying, okay, let's add a fictitious time, and let's introduce a dynamics which has this measure as an invariant measure. And somehow let's use the dynamics to construct the measure nu, because constructing the measure nu is difficult. So the simplest dynamics you can write is this PDE. Okay, it's a reaction diffusion equation with some regularized terms. And space-time white noise. Space-time white noise is needed, otherwise you don't know what is the invariant measure in this case, okay? So here the dynamics is fictitious, okay? It's not derived from microscopic model, okay? But again, it's constrained. You cannot do very much, because if you start to modify this dynamics, you lose control with you lose the connection with the invariant measure, which is this Gibbs measure. And if you lose connection, it's very difficult to establish the two axioms of Euclidean quantum field theory. Okay, so it's quite rigid situation. So the problem is how you take the limit epsilon going to 0 in this equation, and you have even good expectation because you can compute in perturbation theory how the renormalization constant should behave, and it's more complicated. It's diverging with epsilon, and then there is another divergence with logarithm. And then you discover that the Plato-Debush trick, here we are in 3 dimensions, okay, not in 2. You can play the same game in 2 dimensions and the trick will work, but in 3 dimensions does not work anymore. And this was a big problem because what you do then, and then of course, this was actually the first application of regularity structure theory. So in the original paper of Ira in Inventiones, he proposes a main application solution of this quantization, local theory in time of this equation. Let me give you some recent result about that. I see my time is going up. So in all the original paper, solutions are local in time because they are obtained by fixed point without any use of particular structures. And then recent results are Murray and Weber. They prove global space-time solution. And then you can prove ergodicity in the 2 dimensions and convergence of lattice discretization. So you can use this dynamic to prove many things. And you can prove global solution in time, which with a strong property. This is due to the fact that the cubic term is a very strong coercive term. And essentially, solution will enter a compact set in finite time, irrespective of the initial condition. And then there is an interesting paper of Albeverio-Kuzuoka, which in the PD community maybe should be known, because essentially what it's doing is that it proves the tightness for the measure using the dynamics of the PD. Okay, so this is a complete PD proof of a probabilistic result, okay, which is a tightness of a probability measure. I find it very interesting. And then with the Hoffmanova, we constructed global in space and time solution in 3 dimensions, and we also solve equation in 4 and 5 dimensions with elliptic without time. And this is very interesting. There is an interesting conjecture called dimensional reduction, which relates this solution of this elliptic equation to the same measure, nu. Okay, so essentially, solution of an elliptic equation in R5 corresponds to the measure, the 543 measure in 3 dimensions. This is a conjecture which it's done in the physics world, and I don't know very much how to frame it mathematically. And then you can solve some wave equation. Yeah, I think I have 5 minutes, so let me give you a last example, okay? I think I will not have time to enter into the details of how you do it. But I give you another example. So this is population model. So you just have population living on the lattice, and then they diffuse, and then you have, on every site, you have a random environment, and you have some rate for growing or decreasing population. And you take a small variance for this. This is an IAD family, okay? So on every lattice site, you have a different environment. And you take variance of order epsilon square, and you take slightly negative drift, where this constant, so it's going to zero, but it's going to zero in with this logarithm. And you can have, if you take f, the reaction rate linear, you have some kind of discrete Anderson model. And if you take like some logistic kind of reaction rate, you restrict resources. Okay? And then there is a theorem, a recent theorem, which is can be proven with the tool I told you below above, that show that irrespective of what is this function f, in the limit you have a scaling limit, and the limit solves some linear equation. So you see the equation now, it's a diffusion. You need the value of f prime in 0, and you have space-time white noise. You don't have, this noise is not Gaussian, okay? It can be anything, okay? This is called an invariant principle, because wherever the law of the initial noise, at the end you still get Gaussian noise. And it's linear, and you have to subtract an infinite constant. Okay, again, this phenomenon. So this shows you that this equation is not well posed, okay, the fact that you have still infinite constants around. And yeah, so let me, yeah, I think I will not have time to enter. I prepared 2 slides for giving. Okay, let me give you as an example. I will not have time to enter into the discussion, but for example, you can try to think yourself, because this is an easy problem. I mean, think toy problem, which is related to the last example. Imagine you want to give a meaning to this operator in L2. Okay, this is Laplacian plus space white noise in 2 dimensions. Okay, now space white noise in 2 dimensions, I tell you, it's somehow some kind of generic distribution of regularity minus 1 minus k. Okay, so if you look at this operator, you try to think of it as a Schrödinger operator and try to give a meaning of it, you realize the first difficulty you have is that you cannot find any function in the domain. Okay, because if you take a smooth function, it's not in the domain. Okay, because when you multiply with the space-time space noise, it's a distribution. Okay, so you cannot feed to this operator anything and be in L2, anything nice. Okay, the catch point is that the domain of this operator is not made by nice functions. There is no smooth function in the domain. The domain is made by function of regularity 1 minus kappa. And to construct the domain in a very explicit way, you have to use the tools I didn't explain to you, okay? But so that could motivate you maybe to look into the literature, okay? Because then when you use the tool, essentially what happens is that for the function in the domain, the Laplacian and the multiplication with psi compensate to give as an output an L2 function, but so the function have to be very carefully chosen. And okay, it's not difficult, but I don't have time to show you. And so let me wrap up in the last minute. And so what I try to do in these 45 minutes is to motivate the appearance of these singular SPDEs. Okay, they arise as a scaling limit for fluctuation in certain random field. So they contain randomness, they contain nonlinearity, because you have chosen the parameter to be in a regime where the nonlinearity is important. And they are really an effective description of nonlinear, somehow scale invariant, even if they are not completely scale invariant random field, okay? So in this sense, it's a very novel field which open up, which mix a lot probability and PDE theory. Actually, most of the paper are PD theory, from probability point of view, essentially the computation are somehow trivial in most of the cases, so most of the effort is to understand PD theory, but it's not standard PD theory because you work in kind of spaces which are not the standard spaces you see in PD theory. For example, when you work in the full space, you don't have right to work in integrable spaces, okay? Because noise is uniform in all the space, so it's acting in the same way everywhere. Solutions are translation invariant. You have to work with weighted spaces usually. Okay? And this poses problems and questions. And there are various approaches, and I think there are a lot of problems and a lot of things to understand. So thank you very much.
Any question, comment?
How much of this can actually be computed in a computer? By of different kinds?
Yeah, I don't know. Oh, okay. In the two approaches, so in paracontrol approach, what you're doing actually is that you make a change of variable, and at the end of the day, you end up with a standard PD. Okay, so you can use all the methods, for PD theory. In Ira approach, in regularity structure, there is a key result inside regularity structure, which is Ira Reconstruction Lemma, which actually I propose a proof in the proceedings, because I think if you understand this, then everything makes more sense. Okay? And in this reconstruction, so this reconstruction lemma, what it says is that if you know a distribution locally, like some germ of this distribution in a very quantitative way, in a specified quantitative way, then you can reconstruct everywhere, okay? So somehow all this rough path theory, all these theories are about having more detailed look at how a solution looks like. So it goes into the direction of numerical simulation, because in order to provide, for example, convergence of a numerical scheme, you have to understand how the solution looks like and what are the next order. So I would say, I would say that they can be put on a computer without much problems. For example, rough path theory is a way to make more robust the theory of SDEs, okay? So while you don't have much algo, the problem is that, okay, from the analytic side, there should be no problem, okay? The problem is on the probabilistic side, because you have these objects, so, yeah, okay, it's disappeared. You have this polynomial of the noise, and this object somehow has to be constructed a priori, so you need to do computer simulation to construct them, and once you have them, you can use your preferred numerical method to solve the PD, for example. Yeah, so in this sense, I would say effective, but there are two different problems which require different tools.
Any other question?
So in 3 dimensions, it's still a super-enormizable theory, according to the jargon of the mathematical physicist. So do you have any hope to go to the 4-dimensional case by your techniques? Because that's the real problem from physics, as far as you accept that the Weidmann axioms really describe nature, which is also not so
clear.
No,
I think for the boson, for the 5-4, myself, I don't see any way, because, okay, these arrive, 4 is not magical, okay? For example, in 3 dimensions, you could imagine, or in 2 dimensions, you could construct model for which the coefficient in front of the cubic term is 0, and then you have the 5-order term appearing in the equation, okay? And 2 dimensions, you can play this game and have any power. In 3 dimensions, you cannot play any more game. When you arrive to the 5th power, essentially the equation became what Martin Heidegger says critical, okay? In the sense the nonlinearity has the same size of the Laplacian term. And then you cannot, all the way we think about them and solve them is somehow semi-linear way. Okay, so Laplacian has to have the main rule, even if it's not so clear, because we can solve wave equation where there is the role of regularity is less clear. So for me, there is something to understand, but it's clear that for dimension, you cannot expect a finite expansion, for example. So the noise term will be more complicated. There are some RG approach which can handle the measure in 4 dimension under certain conditions, but yeah, I don't know. That's a very difficult problem. It's for, I mean, one of the claim prizes make sense of gauge theory in 4 dimensions, so that's worth.
Other questions? If not, let's send the speaker again.
Thank you.